Hi everyone, today I will speak about Clifford Algebra, which is a special system number tailor-made for geometry. So what is Clifford Algebra? Clifford Algebra is an algebra of vectors. In fact, we must start by a vector space, but in a vector space, you know you can only add vectors, you can't multiply them, and you can only add and scale by a certain number each vectors, but you can't, there is no multiplication between vectors, that's not numbers. And in fact, we can construct for n-dimensional vector space, we can construct an algebra. So then we will be able to multiply vectors. You maybe already use this kind of algebra if you study physics, because what we call the Pauli matrices or the gamma matrices in the Dirac equation in quantum physics, in fact, are a Clifford algebra in disguise. Okay, then for to construct a Clifford algebra, we will need two ingredients. The first one is a vector space. And the second is we need a dot product. If we have these two ingredients, you can construct the Clifford algebra is also called a geometric algebra. Geometric algebra. Geometric algebra is a modern view on Clifford algebras, and which emphasizes the geometrical aspect. Instead of thinking of the number of the algebra like just number, we can see them like planes or point or lines or circles. So it's an geometric view of the Clifford algebra. So maybe you already know about complex number. In complex number, we define a new symbol called I, complex number, I. And I, this is a kind of mysterious number, but what we know is if we square this number, we must find minus 1. This is the rule to define the complex numbers. For example, 3 plus 4i. This is an example of complex number. So in fact, it is maybe a compound number with two parts, the real part and the imaginary part. But this is considered as a number, a complex number. The whole is a complex number. And this I is a special, have a special property. The square equals minus 1. And from them, we can calculate everything you want. Like just number, you can multiply and you can add them. For example, if I want to multiply 2 plus 3i, I want to multiply by 1 plus I, you can use the distributivity. You have 2 plus 2i plus 3i plus 3i I. So what is this new symbol? I multiply I times I. In fact, we can use a special property. We know that e squared equals -1. So it's very important to know the square of this symbol. And now we have 2 minus 3 plus, we can group the I with 5i. -1 plus 5i. So as you can see, we can multiply every complex numbers without problem, knowing this special rule. And complex numbers are important to the Euclidean geometry, because in the two-dimensional Euclidean geometry, complex number will perform rotations. If you multiply by if you multiply by I, is as if is the same thing as performing a rotation on a number which represent a point. Complex number are for spatial geometry. We can represent like a circle. The more you multiply by a complex number, it makes the whole graphism to turn. And we can also define a new kind of number called a split complex number. At this time, the special property we call J, a new symbol, J squared equals +1. So this is a new rule for this mysterious symbol J. And this number are used for the special relativity case, the hyperbolic geometry. So in special relativity, we have time and space. So this kind of numbers, the split complex numbers, will perform the boost in space-time. So it's equivalent to the special rotation in Euclidean geometry, but we have numbers too for tailor-made for the space-time geometry, Minkowski plane. And we can calculate everything you want. 1 plus j multiplied by 2 plus j. So we have 1 times 2 plus j plus j times 2j plus j times j. Now we can use the rule for j squared equal +1. Then we have 3, and how many j's? 3j. This is the split complex algebra for hyperbolic numbers, and we know that with a simple rule about the new symbol we introduce, we can do addition and multiplication. And maybe you've heard of quaternion. Quaternion. So this time it's for 3D Euclidean geometry. And we introduce 3 symbols, I, J, and K, with a special rule for each. I square equal J square equal K square equal -1. So this is the number called quaternions, and it's useful to perform rotation in 3D in graphic engine for a game, for example, for video game. So in fact, we can create a new number system by introducing a symbol with special property. And it seems that these strange numbers are useful for geometry. In fact, we can generalize this construction for any geometry. For example, in 4 dimensions, 5 dimension, we can construct a special kind of number which will be useful any dimension and any matrix. For example, space-time. We have the time +1 for the time, -1, -1, -1 for the space. X, Y, Z. In fact, we can construct special kind of numbers, a Clifford algebra, which will be useful for 3 + 1 dimensional spacetime, or 1 + 3. So how do you construct the Clifford algebra for a certain geometry? In fact, we want, for example, we start with a vector space. For example, 2D, a 2D example, we have the x-axis, the y-axis, and we have orthogonal unit vectors. For example, u sub x and u sub y. And we can write vectors, for example, 1, 2, this one, up, we call it vector v. So the vector v is 2 times u sub x vectors plus 1 time u sub y. We can use a colon notation to 1. So here's the vector space. and we can calculate the scalar product of the vector with itself. We have 2, 1, scalar product 2, 1 is 4 plus 1 equals 5. So now we will construct the Clifford algebra. For each basis vector, we will introduce a new symbol like I or J, but we will call them E sub X and E sub Y. So now that's not a vector, that's a number in your new system of number. For all the basis vectors, we introduce new symbol with no meaning, but we know that they represent the initial vectors. And we want that we have to explain how to multiply these new symbols. So the rule will be that if we multiply, so if you want to associate to the vector v the new number v, it will be easy. It will be just 2 the number e sub x plus 1 e sub y. So v now is a number in our Clifford algebra, and we want that v square must be the same result as the scalar product, the dot product. So we must find 5. So in our new number system, we want that when we square what it looks like a vector, we want to find the same result as the dot product of the vector by itself. So what happens if you try to calculate the square of this vector v? So v square it equals 2 e sub x plus e sub y two times. Yeah. Now we can use the distributivity. So we have 4 ex e sub x plus 2 e sub x e sub y plus 2 ey ex plus e sub y e sub y. And in this new system numbers, the order matter. It's very, you have to respect the order because the numbers are not, we won't find the same result. So what is the product of e sub x by itself? In fact, we know that e sub x square must be equal to the scalar product of u sub x with itself. That's what we want. So we impose e sub x square must be 1. So it is a rule we impose, and now we will have 1. So 4 plus e sub y is the same, 1, plus 2 times e sub x e sub y plus e sub y e sub x. So now there is a problem, because what we want to find for the square of the number associated to the vector v, we must find 5. But we have this symbol here that we don't want. So the rule is that we want this part must be equal to 0. And that will solve our problem. So as what kind of multiplication we can define is we can impose this rule to define the Clifford algebra. So what does it mean? E sub x times e sub y plus e sub y times e sub x must equal 0. And so e sub y x, e sub y equal, I put the symbol in the other side, minus e sub y, e sub x. That's our rule. And this rule is called anti-commutation. This means the order is very important, but if we want to swap the order in this multiplication, we pick up a minus sign in front. So if we want to multiply in our algebra e sub x, y, e sub y, this is the same as minus e sub y, e sub x. So that's our rule. So we have two rules. First rule, we must define the squared. E sub x squared, what is it? For example, plus 1. And e sub y equals plus 1. And the second rule is anti-commutation. So that e sub x, e sub y equals minus e sub y, e sub x. And with these rules, we can calculate everything in the algebra. We can multiply everything. So what happened? For example, I start with a 3D Euclidean geometry. So I define the symbols e sub x, e sub y, and for the z-axis e sub z, and I specify the square of each. E sub x square equals plus 1, e sub y square equals plus 1, and e sub z square equals plus 1. When I will multiply these numbers, I will have, as a result, we can have just a number, for example, 1 or 5. We can have e sub x, e sub y, e sub z. But what happens if we multiply e sub x by e sub y. What is that? This is a new symbol, in fact. We can call it e sub xy. We can multiply e sub x times e sub z. This is another symbol. And e sub y z. So we have 3 more symbols. And we can multiply the 3 x, y, z. So this algebra is a big number. For example, we can have 4 plus 3 e sub x plus 10 e sub z blah 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 plus 14 e sub x z plus 5 e sub x y z. This is a single number. For example, in our algebra, this is a big algebra, and how many number we need, the maximum number we need is 8. So this is a 8-dimension algebra. And we start with a 3-dimensional vector space. And now we construct an 8-dimensional Clifford algebra. And no more than 8, because if we multiply our new symbols together, we won't be able to construct new symbol. For example, if I multiply e sub x and times e sub xy, we will find e sub x times e sub y. This is e sub x squared. So we have a square. This is 1 equals e sub y, but we already have these symbols. For example, if we multiply the last one, the pseudo-scalar, multiply by e sub x, what happened? E sub y, e sub y, e sub z, e sub x. So is this a new symbol in our algebra? Not really, because we can swap the orders. For example, we will swap this one and this one, and we pick up a minus sign in front. And now we can swap this one. So another minus sign occur. And this one is e sub x squared equals plus 1. We find the number e sub y z, but we already know this one, e sub y z. We have it. So we won't produce infinitely many new symbols. So this is 8-dimensional. This is the maximum dimensional. We will have 7 symbols maximum dimensions. So how we can specify a particular Clifford algebra? The notation is CL for Clifford. Then you put the number of positive elements. For example, for space-time, we have +1, -1, -1, -1. So we will put the number of +1 element, and then we put the number of minus elements. 3. Space-time algebra. What is the simplest? So the space-time algebra is 1 plus 3 dimension. This is the vector space. But the algebra is 2 to the power 4. So it's a 32 dimensions. We have the single number, time, x, y, z, time e, x, y, e sub t, e sub x, e sub y, e sub z, or e sub t x, e sub t y, e sub t z, plus e sub x y, e sub x z, e sub y z. So we have 1, 2, 3, 4, 5, 6. 6. Then we have e sub t x y, e sub t x z, e sub x y z, t x z, and e t y z. This is 4, and the last one is e t x y z. So we find 6 plus 8, 4. So it is 16 dimension. Yes, 16 dimension. 1 plus 4 plus 6 plus 4 plus 1. Okay. The simplest algebra, Clifford algebra, will have you start from a one-dimensional vector space, and we have only one positive element and 0 negative elements. So we have just one symbol ex with this property that e sub x squared equals +1. This algebra, for example, we have a example. We have 3 plus 4 e sub x. This is a number, for example, and we know that it is exactly the split complex number. Because in the split complex numbers, we introduce a new symbol j that squared to +1. So in fact, this is the same. The next simplest Clifford algebra will have 0 positive elements and 1 negative element. So we have just one new symbol that's square to -1. For example, 3 plus 4ex is a number, but we understand that this is complex number because the new symbol square to -1, like in the complex number. So this is isomorphic to complex number. And this one is isomorphic to, I don't know, split complex number. This is this way. And for example, we can construct the quaternions with this Clifford algebra with 0 positive elements and 2 negative elements. For example, the quaternion rules are I square equal G square equal K square equal -1. And in this algebra, we have E sub x square equal -1. We have only two symbols. E sub y square equals -1. In the quaternion, we have I, J, K. So where is the K? In fact, we can show, if you know the rule of quaternion, we know that K is Ij. So if we identify I with E sub x and J with E sub y, then K is E x y, E sub xy. So the last symbol is our E sub xy. But can we certify that E sub xy square will equals -1? Let's do it. We have E sub x, E sub y, E sub x, E sub y. We can swap the order. Minus E sub x, E sub x, E sub y, E sub y. E sub x squared equals -1. E sub y squared equals -1. So they cancelled. And we find -1. So it's okay. We have our third symbol, E sub xy square equals -1, which is K. And if we look at the rule of quaternions, we can check this rule. I is E sub x, J E sub y, and K is E sub xy. What does it result? We have E sub x, E sub y, E sub x, E sub y. We can swap the order. We have minus E sub x, E sub x, E sub y, E sub y. This is E sub x square equals -1. This is E sub y square equals -1. -1 times -1 cancel. So we find -1. So that works. This is the quaternion. The quaternion are isomorphic as an algebra with Clifford Algebra 0,2. So Clifford Algebra are very powerful because we can construct system numbers that we discovered over the century and we can construct all this number system for any geometry in any dimension for any metric. It's a very powerful technique. Okay, then see you next time.